Hello everyone, today we talk about Rescue SQL, Oblivier's querying for the Zero Trust Cloud. This work is accomplished by Northwestern University and the Air Force Research Laboratory. This is Xilin Li. First, let's think about the scenario. User devices, such as edge devices, are computationally weak and low power. Hence, a user outsources computation to a cloud service provider. However, a CSP is untrusted. Cloud nodes may deviate from correctly executing the cryptography protocols used to compute query answers. Cloud servers may collude to gain an unauthorized access to users' data. So in this work, the goal is enable users to store and query their data on untrusted CSPs without divulging their records to anyone. Here we use a smartwatch as a motivating example. As a wearable edge device, the smartwatch has limited ability to maintain a large volume of data for the person, such as heart rate, blood oxygen, and so on. Smartwatch is too weak to analyze such physiological data of users. Users would send data from smartwatch to databases of hospitals. However, databases are on public CSPs, which are vulnerable to data leakage. And the hospitals don't want to share data of patients with others while they want to cooperate for analyzing users' data. Hence, it is urgent to have a robust and efficient system to tackle this issue. Thanks to cryptography community, we have strong tool named Secure Multi-Party Computation, aka MPC, to be a potential solution for this problem. MPC allows multiple parties to jointly compute a function without review their private data except the output of the function. Private data are usually protected by secret sharing technique. In this work, our MPC protocols are based on authenticated Garble circuits, and we will also discuss threat model for MPC in the later slides. Now we discuss the main contributions in this work, which tackles the aforementioned problem. The system is named Rescue SQL. Rescue SQL is the first pragmatic OLAP system with all but one malicious security for ad hoc SQL queries. We extend a state-of-the-art, maliciously secure multi-party computation protocol with optimal memory usage and reduced communication overhead. We also demo a user-friendly dashboard with which participants experience query evaluation over the system and explore its detection of malicious CSPs. Before talking about the details of the system, let us go deeper about MPC. MPC protocols need a consistent string of pseudo-random numbers to label wires of circuits in query evaluation. PRN generator under MPC is prohibitively expensive, which could be a bottleneck for the system. Instead, we accelerate randomness generation with a trusted coordinator. We call it trusted coordinator because TC is usually the data owner in our system, such as the user with the smartwatch in our motivating example. TC regularly generates batch of randomness and distributes to each CSP node as input for MPC protocols. Now it is time to talk about architecture of Rescue SQL system. In this diagram, there are two parts. The blue one is the trusted coordinator, which sends SQL queries and the pseudo-randomness to each computing party. The green cylinders R1 through Rn are computing parties, which are CSPs provided by AWS, Google Cloud, or Azure. Recall that we use secret sharing technique to protect private data, so each CSP node holds a partition of shares respectively and jointly computes query queue to produce a share of answer. Finally, TC can retrieve the correct answer A based on those shares from CSPs. Then we discuss the workflow of the system in detail. First, TC has the SQL statement, and it parses the query into a directly acyclic graph of operators, aka operator tree. After that, we use heuristic to generate an efficient canonicalized query plan. The methods include urgently removing attributes that are not needed, leveraging schema information to reduce intermediary cell sizes, or utilizing projection pushdown to reduce columns for join. Then we map each operator node with its predicates to a corresponding cryptography protocol. For example, we know primary key, foreign key of two tables. We assign the node a key join protocol. If not, we assign it a basic join protocol, which is a Cartesian product of two tables, obliviously filtered by a predicate. Those protocols form a sequential secure plan. In the backend, CSP nodes evaluate MPC circuits based on secure plan and the secret shares. Finally, CSPs send shares of answer A for validation and send to TC. Now we are going to talk about the threat model in this work. CSP nodes are malicious adversaries. They can deviate from the protocol arbitrarily. TC is a semi-honest party. It follows the protocol since it is usually the data owner, but it still wants to deduce additional unauthorized information from cloud nodes. The system supports dishonest majority among computing nodes, up to n-1 corruptions with no unauthorized data access, so it's called all but one malicious security. Private input table R is secret shared to R bracket. Party I holds R sub I bracket. Now we talk about experiments. First, we talk about the setup. We have a set of queries in TPCH benchmark, Q1, Q3, Q5, Q8, Q9, and Q18. They are varying levels of complexity with respect to number of operators. We use 4 Linux servers. 1 machine for the TC and other 3 machines are untrusted cloud nodes, up to 2 corrupted machines. We truncate TPCH databases into 3 sizes: TPCH 25, TPCH 50, TPCH 100. Each contains 25, 50, or 100 tuples in customer and supplier tables. We prune other tables corresponding to primary foreign key relationship. First, we test the plain text query and the rescue SQL query. From the table, we can see rescue SQL has 4 to 7 orders of magnitude slowdown compared to plain text execution. We know it's a necessary price to pay for outsourcing MPC on zero trust clouds. Now we go deeper into operator level. We use Q3 as an example, since it contains moderate complexity on number of each operator. From the figure, we can see join and sort operators dominate runtime for the query, which takes 89% and 9% of overall runtime respectively. Others takes minor time, less than 2%. In other operators, we can see project with arithmetic expression, such as calculate the revenue for each row, takes substantially longer runtime than project with merely column permutations. Aggregation, such as the summation of the revenue, also includes arithmetic operations, so it takes considerable overhead to compute over circuits too. Finally, we measure scalability in runtime and the memory. From the left figure, we can see runtime doubles as data size approximately doubles. From the right figure, we can see memory grows superlinear with respect to input sizes. In this demonstration, we provide a dashboard to allow people to experience the system. First, you can select from one of queries in the TPCH benchmark and run it. After that, you can select a machine to corrupt and send a corrupt message to the machine, and the machine will be marked in red. At the bottom of the dashboard, you can see we monitor status of each machine with CPU occupation, memory occupation, and the network condition, and also the runtime. Now we talk about related work for our system. There is a system named STANET. STANET achieves malicious security for OLAP system, but it is the data federation, whereas our address the Zero Trust Cloud. Rescue SQL achieves additional scalability and efficiency with TC. Prior work supports honest majority, but we generalize to dishonest majority. In conclusion, we introduce Rescue SQL and SQL over MPC engine for the Zero Trust Cloud. Trust Coordinator supports query evaluation by providing trusted randomness. The system is malicious secure for at least one honest party among n parties, aka we support all but one malicious security. We also provide a demonstration interface to experience evaluation of TPCH queries and injections of corruptions. Here is our acknowledgments for this work. Thanks for listening our talk.